there are multiple people. So welcome everyone. Funded, so acknowledgement to everyone on the call and as well as everyone else for your respective contributions in helping make that funding proposal successful. So it's great to be able to continue events like this on a monthly basis, the seminar series. This month we have Lucas Hogan and Max Stevens talking to us from one of their offices at University of Auckland. They're going to be talking in particular about the role of digital technologies in reconnaissance as well as assessment. And this is a huge field that's rapidly evolving, and I think it's a significant research direction where we can play a role in collaboration with some of our international partners that have access to some pretty unique digital resources as well. So look forward to hearing the talk from the two of you. Take it away.
Cool. So thank you, Brendan. And kind of what we're going to go through today is a little bit of some experience we've had doing, looking at a number of these recon technologies using a case study building. And I do want to say, I want to definitely say a big thank you to Mo Mustafa, who's on the call here. A lot of what we're showing is Mo's PhD, and then he also did me the benefit of scrambling and getting a bunch of images and slides for me at the last minute. So if we go ahead and share that. Yeah, I guess we'll take it away. And Max, I think you're up first.
Yeah, so our talk today is really going to be talking about how we can make recon broadly, how we can optimize recon more broadly, right? So from identifying the structures we want to look at all the way through to collecting data in those structures efficiently. So there's three main topics we're going to talk about. The first thing we're going to talk about is my experience in Wellington immediately following Kaikoura. So we'll briefly mention that. The second thing we're going to talk about is using near real-time impact frameworks to identify and prioritize structures that we want to look at or perform recon in to gather data from. And then the third thing we're going to talk about is how we can optimize our data gathering methodologies to give us adequate information so that we can diagnose what's happened in the structures we're interested in. So with that, we're off. Hopefully. Oh, there we go. So Kaikoura Earthquake, as most of you are probably aware, the Kaikoura Earthquake happened in November, I believe it was November 16th of 2016, in the middle of the night. I remember the day after it happened, I was sitting in my cubicle in the Newmarket campus here at the University of Auckland, and my advisor, Ken Elwood, ran in and he said, "Oh my gosh, did you hear what happened?" And I said, "Yeah, there was an earthquake in Wellington." And at the time I had been working, just really getting into this Smart Seismic Cities project in Wellington. And so we decided that since I had some knowledge of the building stock in Wellington, that him and I should go down and try to perform some reconnaissance to see what had actually happened. And when we got there, so later that day we were on a flight down, and when we got there, things were super hectic. We're like, oh my gosh, what do we do? Where do we go? And so Ken had set up a bunch of meetings with a bunch of engineers, people at WCC. We're scouring the news sites to figure out where to go. And basically through word of mouth and reading stories on the internet, we were able to identify some buildings that we could look at, or that we wanted to look at to perform some reconnaissance in. Actually, I remember at one point we had heard that there was some damage in a building behind the Amora Hotel. So we ended up wandering around in the parking structure back there, just randomly looking at damage in shear walls and columns. We heard there was actually damage in the Amora Hotel, so we wandered around in there until they politely asked us to leave. So yeah, it was a very chaotic time in Wellington immediately following the Kaikoura earthquake. And so finally we did get into some buildings, and once we did, it was like, oh my gosh, look, damage, what do we do? So me as a fresh 20-something-year-old postdoc with a camera and a notepad, just frantically started taking pictures and jotting down notes. So these are just some of the pictures from one of the buildings that we were able to get into. You can see, look, crack in the ground outside. Oh, look, I don't even know what I was trying to see through the windows of that second picture on the top. But what's really important to note from these pictures is I'm running around taking all these pictures, and I took hundreds of pictures. I filled up almost an entire notebook full of notes. But when I got back to my office, it was like, holy cow, what do I do with all this? How do I put all this together? There's not very good, reference between my pictures and my notes. I can't tell where I am in these buildings. It was really a mess. And so The challenges are, as I just talked about, are once you get to the region where the earthquake has happened, is where do you go? How do you identify the buildings you want to look at for reconnaissance? The second is once you get back to your office after you've taken all the pictures and taken all the notes, you want that picture on the other side of the column. You want that picture on the other side of the beam that you don't have. Third thing is scale. I'm looking at these pictures and I can't tell how big things are. I haven't held a pencil up. I haven't held a tape measure up. And then there's, obviously time. You want to limit your time because you're exhausted and you want to make sure that you're safe. And then later on, you want to focus on archiving data and things like that. So what can we do to optimize this process? Well, there's two things we can do. One thing is we can use near real-time impact frameworks to prioritize structures we want to look at for recon. And I want to emphasize here, so these NRITs can be used for a few different things. One would be to identify structures for rapid structural evaluation to make sure they're safe. What we're talking about here is using them for recon, identifying what buildings we want to perform recon in. And then the second is using state-of-the-art, and I say to us because a lot of this stuff actually isn't state-of-the-art anymore, reconnaissance tools such that we can gather the information we need after the event. So the first thing we're going to talk about is near real-time impact frameworks for reconnaissance. Now, I want to note that near real-time impact frameworks are not new. There's a number of them around the world. There's HAZIS in the US, PAGER in Taiwan. But essentially what they all have in common is they provide situational awareness following an event. So if you have a building stock, let's say in Wellington, like shown on the right here, it can give you an idea of how the different buildings performed following the event. So there's two things that you need for any near real-time impact framework. The first is a measure of demand, and the second is structural response models. So for measures of demand here in New Zealand, there's three main sources of data. The first would be the GeoNet strong motion stations. So you can see on the right here in Wellington, those are the GeoNet strong motion stations currently down there. The second, CSI, Canterbury Seismic Instruments, has a current initiative where they are developing dense instrumentation arrays in urban areas in New Zealand. So hopefully those can fill in some of the gaps between the GeoNet stations. And then finally, how do we just, and then there's also synthetic ground motion, but that'd be more for scenario planning. So once you have that, the next important thing is how do we distribute the demand? So if we go to the next slide, you can see we have all these buildings in Wellington. So this is the Wellington Structural Database. How do we get the demands from those instruments to those buildings? Well, you might say, why don't you just put the closest building to the closest instrument? And well, that may work in a city where you have fairly consistent ground conditions. Here in New Zealand, particularly in Wellington, that's not going to work. So what we've done, if you go to the next slide, is we've linked all of our buildings. Oh, thanks. We've linked all of our buildings to the strong motion stations based on site period. And what you can see here is what happens is we had this nice distributed instrumentation array here in Wellington. What ends up happening when you distribute those demands based on site period is, holy cow, my red and my blue stations are suddenly doing some seriously heavy lifting. Okay, and we actually have a proposal in to try to figure out how to optimize this instrument placement based on site conditions. Anyway, cool. So now we've linked the demands to the buildings. What do we need to do next? Well, we need to generate a response prediction model for each building. Okay, and what that does is it estimates the damage or response to the building based on the intensity measures of the ground motion. And there's a range of ways to do this. All of the NRITs around the world kind of do it a little bit differently. Some will use the capacity spectrum method. Some will develop finite element models for all the buildings. But what it all comes down to is you want to develop a model capable of estimating the response of your structure subjected to that ground motion that we've now linked to that intensity measure gathering tool, e.g. the strong motion station. So there's a few ways you can do it, and I'm going to introduce this SDOF method just because this is what we've developed in Wellington. But you can essentially develop an SDOF analysis where all you do is you look at the design spectral acceleration at the first period of the structure and compare it to the measured spectral acceleration at the first period of the structure. Using analysis like this is fairly efficient. You're only looking at a couple of numbers for each building. You can run the analysis very quickly, and you don't need all that much information about the buildings. The second approach that I have shown here is an MDOF analysis. This is a much more complex approach where you essentially develop finite element models for every single building in your region of interest. But this can be very time consuming. You need a lot of data to build the models. So building the models can take some time. And then if there's an event, it takes some time to run the models. And just to pitch a project that I'm working on right now through EQC, what we're doing is we're developing a machine learning driven framework for Wellington, which will hopefully give us a very accurate response prediction estimate of all the buildings in the Wellington region almost instantaneously following events. But that's not really the focus of this talk, so I'm not going to talk too much about it here. But I've recently made some pretty interesting, what's the word I'm looking for here? Progress, that's the word, on this project. So there's more to come, so stay tuned. So we're not quite here yet. But what we have developed, like I said, is a 1DOF Wellington framework. So we've linked all the buildings in Wellington to the strong motion stations based on the site period. And then we're able to compare the design accelerations based on the year of construction to the measured accelerations from the strong motion stations. And so what I have shown here is actually, there was an earthquake earlier this year in Foxton. This is a serviceability limit state ratio for the buildings in the database. Okay, and so the next question is, let's say we've identified these buildings here as buildings of interest for reconnaissance. You know, they're getting pretty close to their serviceability limit state. What do we do when we identify these buildings that we want to look at to perform more detailed recon on? And with that, I'll pass it off to Lucas.
And so if we're going to go through these, you know, we've got lots of options. And like I said, well, this is going to look at a state of the art, but really state of the art to us. There's a number of industries outside, folks who are focused on earthquake engineering, who've been using these technologies for a long time. So, you know, there's lots of cool things out there, and some of this might be helpful. So you got drones. Boston Dynamics is coming up with the really slick spot robots, but you know, some of them might not be so helpful. You know, they might be too complicated. There might be a lot of issues around what we are and aren't allowed to use in a given area, given privacy, given access, all of those things. So what I want to walk through is a little bit of how we've approached this on this case study building. And most of this is really to just kind of show you the process that we went through and try to highlight some of the pitfalls that we came across. So the first thing we want to look at is, you know, what we've all done previously where, you know, this is, and Max had mentioned this with Kaikoura, show up, there's building, you got a camera, what do you do? So the tendency is to go, hey, look, there's a crack. Cool, that's really neat damage. But, you know, at the end of the day, you'll go through, oh, there's more pictures, more pictures, more pictures. What do you do? How do you sort them out? How do you know where they're from? And so, you know, just some really straightforward things, which you don't need any big complicated technologies for, is just knowing how to organize yourself and your data. So the first thing you're going to do is you got to take a visual record of where you are within the structure. So that could be, or in what the structure is. So if the building has a name on it, that's great. If it doesn't have a name, find your nearest intersection. And then once you've done that, you need to take, you know, what are called establishing shots. So, you know, we've all seen these. If you've seen the movies or TV, it's anytime before you go into a scene, there's a shot of the overall area. So in Seinfeld, every time that they go from the apartment to the diner, there's always a footage of the exterior of the diner. And then once you're there, take your photos, and you can do this sort of at a different hierarchy where you can, you know, like what I've got here is we've got an establishing shot of this column. And then our orientation is, because this building was going to get knocked down, we could just write all over the walls. So we wrote what column it is relative to the grid lines of the building. If you have drawings, fantastic. If you don't, and then you're not allowed to write on something, well, bring a whiteboard or bring a piece of paper, bring something where, because you want to link that with your photos, you're more likely to keep all your photos together, and you're less likely to keep your notes with those. And then once you go in, take your picture of the area of interest and do it with scale. So you can see these numbers here are crack widths, but you could do that with a ruler, a pencil, a phone, all these things which, you know, have relative scale. And so these principles which you use with just a normal camera follow the same process with these new technologies. So the first one we want to look at is structure from motion. Or photogrammetry. And essentially what this is doing is you're taking a bunch of 2D images running around your thing of interest, and they stitch together a 3D model. So I've got just a quick little video. This was a beam that was in our lab. I see Tayo's on the call, so he'll recognize this beam. So before we went down to the building, we're like, well, let's just see if we've never played with this technology before. Let's see what we can see and how useful it is. And, you know, it is, you know, relatively, here's just a still from that model. It's pretty good resolution. So when we go through, for prep, what we do, as I said, you want to have, a nice clear area because you need to try to walk around the structure and keep more or less the same distance and the same image quality, exposure, and all of that as you're moving around. Because what these algorithms are doing is they're just comparing pixels together. And if they have a pixel which is similar, they go, hey, that's the same spot. And so they'll stitch your photo together appropriately. If you've got wildly different lighting, they can challenge. The other thing that helps is, again, we could draw all over the floor. So these cracks are this nice random array of pixels as far as the camera and the algorithm are concerned. So there's lots of places for it to stitch together. And you can see we've also glued on these targets. And from those targets, you can pull scale, because when the structure for motion stuff, it doesn't know how big a thing is. It's think of it like a vector image for like Photoshop or for a PDF. It just knows relative geometry. So one of the challenges with these columns that we ran into, so you can see that we've got this small bit of facade with a small distance to the facade here. So that's about as far away as we could get. So we had to use a really wide angle lens in order to get everything in. Also, we've got the exterior here, and then there's no power in this building, so it's much darker on this side. So we had to do some supplementary lighting. You can see Max playing tripod there. And then what you do is you just literally walk around and you take a whole heap of photos. And then you end up with something like this. So each of these triangles is a location where there's been an image taken. So in order to get a decent model picked together, it's about 70 columns per image. And so you can see basically everywhere where Mo stood, took an image at different angles so that you could get this whole thing stitched together. And then, just showing you here on the right, some of the challenges with this. It's, it's not necessarily turnkey. You do have to make sure that your exposures are right, your overlap is right, that you're not, doing things like zooming in and out on the image, or else you'll end up with these big holes and these big sort of bubbles coming up on your model. So, that's just using a DSLR, but, the same principle applies for really any camera. So we wanted to, while we had access to this building, we wanted to try a few different methods, basically using the same technique. So the first thing we want to do is drones. Drones are great. They're cheap. They're easy to get. They don't like flying indoors. So your commercial drone relies really heavily upon GPS in order to stabilize. So if you're inside, you're not going to get that. So you have to compensate by having a decent drone pilot. Jeff had flown this drone for about 4 hours over the last month before this. So none of us there were experienced drone pilots, but we did learn quickly. It was a lot of challenge. The big reason we used it was, we had these big atriums. We wanted to see what was going to happen over here. Well, we can't, we can't stand over here unless we're going to Wile E. Coyote it. And so that was where there was some use. I will say, flying in here, and we tried to go in between the columns. So in between here, you get lots of prop wash and really challenging for the little drone to stabilize itself. Again, where it's super useful is exterior shots, places where you're going to have difficult access. So, parts of this are using the tool, as it's appropriate. And so we're like, well, we're really interested in the floors of this building. Well, let's see what we can do. The roof is off, so now we've got a GPS signal. Can we do the same thing, but basically pretend that we're indoors and just see, well, can we do these sort of preset flight paths and everything else that the brochure said that we could do. So things to note, you are an aircraft, so you need to have air share. Max will tell you, there's lots of challenges making sure that the drone knows what the ground is when it's level, and it doesn't go shooting, 40 meters from the ground is different than 40 meters from the top of a building. And then the big one is, you'll find this out pretty quickly if you're anywhere near the water. Seagulls hate drones, and they will come and start dive bomb them. So that was that one. The other thing we tried is, like I said, we're really interested in the floors and we want to try to keep the same distance and good overlap. So we tried this, and that might be a little hard to see what we're doing in this image. So that one will be a bit easier. It's basically, I'm sitting there as a tripod and as a trigger, taking pictures, and then I have my two spotters here on our super safe dolly here are moving me approximately half a meter each time, take another picture, move half a meter each time. We did finally get it a little bit more optimized, and so we could do it with just one person. And with that, again, you see we need supplementary lighting, all those things to try to keep it even and consistent. And then you end up with something like this, where you actually have this really nice high resolution image of the floor. You can see that it's curved. Again, this is because we don't have any control points on there telling the model that, hey, no, you need to be flat. Part of that curve is also coming from the fact that, like I said, we're using a really wide angle lens. So I think we were sitting at like a 12, somewhere like a 10 or a 12 millimeter focus length. So it's quite wide in order to get that coverage. And so because of that, you've got a lot of distortion in it. So you'd have to correct. I guess one final thing to talk about with the structure from motion, which is really important, sort of the pro tip, is make sure you take your images in RAW format instead of just a straight JPEG. And that means that you can go back, you can edit, you can adjust, just like you were doing while taking the pictures in the camera. But you can do that post-process. So it's a bit more forgiving. If you just take a straight JPEG, you're stuck with what you're stuck with. All right, moving on to our sort of final technique will be these laser scanning. So laser scanning, we've got some images up there, other folks. So you see the Harbor Bridge, which is some stuff from Harrison Greeson of the Auckland Ferry Building. But essentially all laser scanning is doing is it's doing a line of, sending out a line of laser beams, and then it's got a sensor and it's coming back and it's determining, basically travel time on there. And with most of them, they've got a 360 by 300 camera, degree camera. So you can't see 60 degrees where your tripod is. So you can get this full sort of 360 HDRI image. So, what did we do? We wanted to try, well, there's all these different scanners out there. Some are cheap and some are really expensive. So we tried, 3 of the low cost budget ones, see, well, are those suitable? And there's only one button on them, so they're pretty easy to use, versus sort of a mid-range one, which is a little bit more expensive per day. And so we went around and we took a whole heap of scans, so about 1,000 of them. A lot of scan projects are about 10 to 20. So this was a tough one to learn on. So you can see us in there scanning, basically waiting for it. And it's between 3 to 5 minutes to do a full scan. So you can see all of that time does add up. Again, just a little bit of a video of our output here. Where the real advantage of this is we do have something which is dimensionally accurate. Like any of you who are familiar with surveying, you do want control points, linked back to a datum to make sure that you do lock in all of your geometry. And, those little tiny squares which we had were very much ways where we could, help tie multiple scans together. And so this is just really going around looking at each of those 360-degree images. And the nice thing on this, it's like time travel. So we're pretty much just going back. We have a look and like, well, where was that damage? What did we see? We can quite easily go in between floors to see if things propagate through. And you see every time that we go to one of these different circles, which is a scan location, you'll see it gets pixelated. And that's really the point cloud map that's coming through. Just for the sake of time, we'll just kick through a little bit faster. But you can see, we saw damage which we hadn't seen and tested before or in other buildings, and this allowed us to be able to go through, and by us, I mean Mo, to be able to go back through and see, well, where does this damage occur? How often does it occur? Do we see patterns? And then, you know, we'll just flick through real quickly some of the outputs. So not only do you get the images and the point cloud, you can also pull out the color intensity of the laser jumping back at you, which is useful for things like cracks. And you can do stuff like look at what your floor settlement is. Because we're structural engineers and do work with concrete, oh boy, do we love cracks. So here's a scan of the floor. And you can see this is the hole here is where there's a column, so it's not going to be able to scan in the column. And you can see these sort of spider web things are the cracks. Some of those are getting picked up because there's a big color difference from where we've marked them, and some are, you know, there's great big cracks, and so you get a different reflection. So we've been working on crack detection. As you can see, it seems to not be able to detect the biggest cracks in there. So this is definitely a work in progress. So the promise is there, but it's a challenge. So the final little bit here, the last few slides are just how do these things stack up together for a number of bits. So in terms of resolution, the structure from motion by far the best we can get. So we get down to quite small cracks. That makes sense. It's this really high resolution camera, lots of images, while these 360 cameras coming off of the scanners are going to be sort of, you know, your 13, 15 megapixel and then stitched together. So, but even there, they can get about 1 millimeter, which to be honest, for big damage, that's about all we're going to look at and all we really care about. In terms of how long things took to use, because this is really important for if you're going to go out and do this, is there's going to be time. So the cheap scanners took about, you know, to do one floor, took about 1.5 hours with 3 scanners, and you had 2 people moving them around. For the mid-range scanner, you had about 2.5 hours. This one was nice because it could keep track of where it was relative to the other scans, which helped with post-processing. And the structure from motion by far was the one that took the longest time, just because you're taking so many pictures manually and it's a slow process. Other things which were sort of eye-opening was, you know, you collect all this data on the machine, you got to get rid of it. So the structure from motion, we're all fairly familiar with this. We've all taken, you know, images off of an SD card, about 3 hours, just because we had gigabytes and gigabytes of images. The mid-range scanner was, you know, similar for given the amount of, you know, the terabytes we're pulling off. That was about 8 hours to pull off all the scans. But the cheapo ones, because it was a Wi-Fi transfer only, it was basically real time. For as you took the scan. So it took a week to get all 3 of them off. That was a right nightmare. And then the other one was post-processing. So these, you know, really big, heavy data sets. And so, you know, just using equivalent to a laptop. So kind of a consumer grade machine, structure from motion, maybe about 4 hours per column. Stitching together some of the mid-range stuff, about 2.5 days. And then the post-processing on the cheap ones took a long time because Mo had to go through there and manually say, basically plot them in 3D space using his notebook to try to keep track of everything. So I guess just sort of concluding remarks, you know, we're working on new ways to do these frameworks. The existing tech we have is actually really good. And, you know, the big part of this is trying to make sure that you are aware, you organize before you go out. These new techniques have a lot of promise, but there's a really steep learning curve. So if you're planning on using them to go out and then do recon work, make sure that you've spent some time with them before you head out. So with that, any questions?
All right, thank you guys for the great overview in a compact amount of time. Questions from people, and Pavan, maybe feel free to ask your question verbally that you've just written in the chat as well, if you can.
Oh, so Pavan wants to know, we collected all this data, how much of it was useful? Well, this is always the issue when you do data collection, because you're like, there's a finite amount of time, and we do tend to run under the premise of it's hard to collect and sort it out now, it's impossible later. in terms of what's useful, I mean, those laser scans have been, the fact that we did all of that work, that's been really eye-opening and really been very, very helpful in terms of our ability to go back, reinterrogate this data in a level of detail we wouldn't either anyways. And because we were going in and out, we did so much prep on that building. I think we were maybe 2 or 3 weeks of just painting cracks in it. Every time we went in, we'd go look around and we learned something new and had a deeper, richer understanding every time we went in there. And so, you know, this sort of scan technology allows us to do that while sitting in a comfortable chair and with a cup of coffee. And so I'd say all of that has been really useful. The structure for motion stuff, hit and miss. I mean, you know, it may be part of what makes it, you know, questionable is we haven't worked out our workflow and our pipeline on how to actually analyze it in a efficient way. We haven't, you know, we're hoping to do some stuff using sort of existing machine learning algorithms to pick out crack detection and all of those things. One thing I didn't tell you, and one sort of benchmark, you know, one part of the building, we did really detailed crack mapping like we would for a specimen in the lab. And then the other part, we did nothing. Sort of similar levels of damage. And we wanted to see, well, what can you see when you've, you know, combed over it and know in a lot of detail where all this damage is, and what can you see just sort of straight from the work.
Hi guys.
Go for it. Go for it.
Yep. So my name is Shannon from GNS. So we also did a lot post-event survey, and so first, I mean, you guys have did a quite interesting and excellent job. So I have couple kind of practical issue. So the first one is, I think it's quite challenging to get the permission to go inside the building you want to survey. So maybe you guys can comment on that. And the other one is, in your case study, pretty much all the carpet partition furniture being removed. So you can see the crack on the floor and the damage on the column. But in reality, probably you will have all the stuff mess everywhere, right? So how this kind of technology can be used? I mean, yep. Before we have the clean house for you to do the damage survey.
Those are fantastic questions. I'll speak to the access one first. So you'll see this for, and I mean, this is kind of the same for any structure you're going to do recon on, where you're going to need to ask permission to go in. So I don't think so this isn't necessarily you're going to do this on every structure and everything else. This is, you know, often these are structures where you've seen, and remember, this is reconnaissance work really focused on research or detailed damage assessment, not for response. So this isn't for, you know, civil defense, what's happening. This is really, we know there's been damage in this building. We want to look at it in another level of detail. So that process of getting access will be the same. And this is one of the reasons we wanted to discuss, you know, how much time all this stuff takes, because your time and your access will be different for every building, every structure. In terms of the non-structural, again, you're 100% correct. One of the reasons why this building was such an attractive case study is because it was getting demolished and they were going to do a soft strip first. So all the non-structural was going to come off. So we rarely have an opportunity to see, wow, the building is as open as we'll ever see it, and actually really get a good understanding from a structural point of view. So while, you know, you might have in a normal building, you're unlikely to get all of that strip out, you'll probably have areas where you'll be able to remove non-structural stuff. So you don't necessarily have to do these things on an entire building. You can do all of these processes on a small subset. And this is where, you know, if it's smaller, something which is a bit more time intensive, but better detailed, like structure for motion, might be a better tool versus some laser scanning. Or if you know that there's going to be a wider damage bit, well, laser scanning might be good. You also might be working on a bridge. Yep. You might be working on a landslide. You know, these are all, they're not necessarily, you know, restricted to only buildings there.
And I'll just follow up from my experience in Kaikoura. Some of the buildings that we went into after the event that weren't necessarily totaled, that were going to be repaired, we were able to rip up the carpet and, like Lucas said, select areas. So some of these technologies would still be useful. You can knock down ceiling tiles and rip up carpets around columns and things of interest. Obviously, you can't do the entire building, but even in really localized areas, they could still be useful.
Cool. So guys, maybe we'll catch up during the coming QuakeCoRE meeting in Nielsen. Cool.
Quick question from me. Where do you guys see these technologies? I mean, you've given us a picture of what the current technologies can do now. Where do you see these going in the near future? And I guess my two initial thoughts to prompt that are cases where you kind of alluded to it, Lucas, where you're using machine learning to automatically process the data. So you're avoiding the question of data overload, kind of the equivalent of search engines on the internet. And the second one is using robotics by combining drones to actually collect the structure from motion data so that you're not having to manually stand there for an hour and a half and do it yourself. Any other thoughts that are kind of, from your guys' perspective, immediate needs or possible pathways where things are like that?
Well, I will say you hit on the things that we were sort of, and this is one of the reasons why we threw a drone in the building to see, what can we do? We've been thinking the same way. I think that, in terms of where is this stuff heading, is the barrier to entry as a user is just going to get lower and lower. I mean, the structure from motion things now, there's phone apps where you can take your iPhone and scan your head and you get a 3D model. One of the challenges that we'll face for our use case is taking things which have been optimized for facial recognition, some more consumer driven bits, and seeing if we can apply them to what we want to do. But I do think that, they will just get easier to use. And a lot of so it's like a lot of the stuff we work with, in other fields, it just, the need to be an expert and the need to know all of those little tricky bits in order, you'll still need those to get that last 90, to go from 90 to 100, but to get most of what you want will become easier and easier.
Yeah, and it's definitely not quite there yet. I mean, every time we've taken the drone out in the field, we've had problems. We recently went down to Farrakina. We brought this giant, really expensive drone, couldn't get it to fly. We had some close calls with the drone we were flying.
We had some colleagues came down. It was the same day that the Harbor Bridge got wrecked. So it was windy and the little consumer drone was not going to fly in that. The next day it was raining.
Yeah.
It's not waterproof. It wasn't happy. So it's impressive what you can do, but I do think that the really important thing is, one, to get some practice with this and understand where the limitations are, so that you're not having to, you go, oh, technology, cool, we can do this, and just hop in and spend all your time trying to learn how to do these things while you're trying to get real work done.
Yeah.
Great, thanks guys. Any last questions from anyone on the call?
Yeah, James.
You're a little bit low, maybe come closer to the microphone.
Oh, it's right at my mouth, so maybe I just shout. Is that better, Brendan?
Yeah, we might be able to make it out if you continue.
Okay. It's James Russell here from Tonkin and Taylor. Really nice presentation, thanks guys. Can you hear me, or is this?
Yeah, no, we can just get you.
Okay. I was really interested in some of the basics of what you were talking about. The basics of camera use for reconnaissance. Is there anything that's been published in and around that would just be really useful for some of the junior people we have who go out and do reconnaissance on?
So it was a question around camera specs in terms of minimum resolution and things like that.
We actually didn't find it to be a big limiting factor. And this is where, I mean, the more you get into photography, unless you're going to do, so obviously the higher resolution, the smaller amount of, you can actually get with an individual pixel. So I think we were using just sort of a consumer grade 20 megapixel Nikon. So it was a real sort of middle of the road, sort of your like $800 camera. So we weren't spending 10 grand for a camera. But, you know, I've seen good structure from ocean work done with a cell phone. And in fact, in some ways, the cell phone's better because you've got a consistent focal length. So those type of things are, I think, less of a barrier. And, you know, the more and more that you look at with digital photography, so the physical sensor is one part, but it's the image processing is more and more a big issue. Actually talking about, there we go. So published in terms of sort of tips and tricks on how to do this.
Yep.
Well, I know this session is being recorded.
We have the conference paper coming out, I'm not sure.
Yeah, I don't know that has that level of
We might have just found a hole in the literature, and we'll get on it.
Lucas, I can pass you James's email, or he can reach out to you directly. You guys can chat further.
Excellent.
Awesome. Okay, well, thanks everyone for joining the call, and particularly.
I have a question.
Oh yeah, sure, go ahead.
I raised the hand here, but so, well, first of all, thanks for this great work. I've done a little bit of that, like drone fly and laser scanner, and I know the pain that it could be. So I really appreciate that massive work that you've done. But I have one question, because yeah, we always use drone for photogrammetry and then LiDAR for the point cloud or for directly measuring. But how easy, or do you know how easy it is to access to have a drone with LiDAR in it?
Well, I think that so you got to remember, Paco, that, you know, LiDAR was really pioneered off of airplanes.
Yeah.
So there's nothing to say you can't. I think the challenge becomes payload. And I think the other one is the market. I know that there are some drones that use LiDAR for the navigation. I've seen stuff where, and particularly the ones which are set up for indoor use, I've seen stuff where they're basically flying through, you know, subway tunnels in New York and various places where they've got construction crews there, and they've got, say, potentially a hazardous gas, and they don't want to put someone in there. So as a platform, there's nothing to really say that you can't do it. I think that the challenge that you'll find is finding something at the price point that you want.
Yep.
And particularly if you're just starting to learn all of this stuff, which, you know, I know definitely here at Auckland, that's where we're at. It doesn't seem like the right way to go yet in terms of finding that, because we don't know where our needs sit. But there's nothing really that seems like there's an impossibility with that.
Okay, we should probably stop there given the time we're at. So thanks, Lucas and Max, once again, and look forward to seeing many of you again for next month's seminar. Thanks, everyone.
Thank you.